Welcome and thank you for joining tonight's quiet journey through the deep space between our Sun and Alpha Centauri. In this episode, we drift through 70,000 years of darkness, explore the violent heart of a tiny red star, and follow the impossible dream of crossing the gulf to our nearest neighbor in the cosmos. If you enjoy falling asleep to calm science-filled stories like this, please gently tap like, subscribe, and turn on the notifications, so this peaceful corner of the universe is always waiting for you at night. Across the neighboring abyss, the familiar map of the solar system quietly recedes until it becomes a single bright island floating in a wider dark. In that island, all recorded history unfolds in a thin film of air around a small blue world circling a modest yellow star. Within that island, distance still carries a human scale. Light needs just over 8 minutes to cross from the Sun to Earth, and signals crawl between planets in spans that fit inside a lifetime. Robotic explorers fall toward Mars in less than a single year. Probes slip past Jupiter in only a few years. Even the long arcs towards Saturn and the icy dwarf planets, though slow, remain stories that can be told from launch to arrival within one generation. The illusion begins to soften as the scene gently pulls back. The orbit of Neptune shrinks to a ring. The scattered comets of the Kuiper belt blur into a pale halo. Far beyond the distant reservoir of the Oort cloud stretches outward like a ghostly shell, enclosing the solar system in a sphere whose edge no spacecraft has yet approached. Outside that invisible shell lies the domain that truly deserves the word abyss, the space between the stars. Across that gulf waits the nearest other system, Alpha Centauri, a small knot of light, a little more than 4 light years away. On star maps it appears almost comfortingly close, yet the phrase light year carries its own hidden weight. A light year is not a span of time, but a measure of distance, the length that light covers in 1 year of unbroken flight. Light leaves the surface of the Sun and crosses each second with nearly 300,000 kilometers behind it. In one uninterrupted year of travel, it traces almost 10 trillion kilometers of emptiness. Multiplying that distance by a little more than 4 to reach Alpha Centauri yields a figure that escapes ordinary intuition, a number written as a 4 followed by 13 zeros, a distance that resists every attempt to anchor it in daily experience. To soften that scale, imagination turns to models. In one of them, the Sun is reduced to a sphere that could rest between human hands, and Earth is placed at a distance of about 1 meter, a single step across a quiet floor. At this scale, the outer planets fall into place along a long hallway. Jupiter lies several meters away, Saturn farther still, and Neptune occupies a position near the end of a large building. The entire known architecture of the solar system, from the orbit of Mercury out to the frozen dwarfs, fits comfortably inside a city block. In such a model, the question arises of where to place the nearest other sun. Proxima Centauri, the closest member of the Alpha Centauri system, would not hover above a nearby street. It would have to be placed hundreds of kilometers away, far beyond the model city and the surrounding countryside, distant enough that a fast car would need several hours to drive from the miniature sun to the miniature neighbor star. The solar system becomes a glass marble at the center of a continent of darkness, and the next star is situated on the horizon of another country. That simple mental image quietly alters the feeling of the 4 light-year gap. The smallness of the number dissolves into the reality that even the most ambitious machines humanity has launched are barely moving against such a scale. Voyager 1 has been falling outward for decades, coasting now through the outer darkness at a speed of roughly 17 kilometers per second. In planetary terms, that speed is impressive, yet when that same motion is projected onto the journey to Proxima Centauri, the timescale expands into something almost mythic. At that steady pace, a direct trajectory toward the nearest star would require on the order of 75,000 years. That number stretches far beyond the span of written memory, back toward Ice Age landscapes and forward into futures where languages and cultures may have shifted beyond recognition. A spacecraft departing the solar system today on such a journey would arrive in a time so remote that the civilization which launched it might exist only as a thin layer of artifacts in distant geology. This is the neighboring abyss, a gulf that is numerically modest yet existentially vast. In that gulf, distance and time fuse into a single barrier. Across tens of thousands of years, continuity frays into fragments. The crossing no longer belongs to individuals or even to societies, but to a long chain of generations or to machines designed to outlast the cultures that built them. At the imagined edge of the solar system, the light of the sun already dims into a bright star among others, and Alpha Centauri shines as a slightly shifted point in the same river of light. The empty stretch between them holds very little matter, only thin gas and rare dust grains scattered across immense volumes. Yet that same emptiness functions as a wall, not because it contains something, but because it is so nearly nothing. In that almost pure nothingness, the familiar tools of travel lose their power. Rockets that have carried probes to every major planet are revealed as local ferries working in a shallow bay while the ocean beyond remains untouched. The neighboring star system stands on the far side of that ocean, visible and measurable in its basic outlines, yet separated from the solar system by a span of space and time that transforms a nearby companion into a distant, almost unreachable shore. An island of 3 suns hangs in the darkness just beyond the reach of the solar system, a compact knot of light that from Earth appears as a single bright point low in the southern sky. To the unaided eye, it is simply Alpha Centauri, the nearest obvious star beyond the sun. Under magnification, the point slowly separates. First it breaks into a close pair, 2 stars, so near together on the sky that they seem almost to touch. With more careful measurement, a third, much fainter companion enters the picture far from the other 2, yet drifting with them through space. The nearest stellar neighbor is revealed not as a lone sun with planets, but as a small system of 3 stars, sharing one broad gravitational well. The 2 main members, Alpha Centauri A and Alpha Centauri B, resemble the Sun more than they differ from it. Alpha Centauri A is slightly more massive and more luminous, with a surface temperature that produces a white gold light similar to that of the solar system's star. Alpha Centauri B is somewhat smaller and cooler, giving off a softer, more orange glow. Each is a stable middle-aged star, quietly fusing hydrogen in its core. Their true strangeness lies in their relationship. Rather than orbiting alone through the galaxy, they revolve around a shared center of mass, a balance point in the empty space between them. Their orbit is not a simple circle. It is an elongated ellipse that carries them from comparatively close separation to much wider spacing and back again. One full loop takes about the span of a long human lifetime. Over roughly 80 years, the 2 suns complete one slow turn drawing together and then apart in a rhythm that repeats many times over their long existence. At closest approach, their distance is comparable to the region near the orbit of Saturn in the solar system. At their farthest separation, it resembles the span between the Sun and the outer dwarf planets. For any worlds orbiting close to one of the stars, this slow breathing of the binary would be a background cycle, altering the brightness and position of the companion sun over decades. In the sky of an imagined planet near Alpha Centauri, A Alpha Centauri b would appear for many years as the brightest star, then slowly swell to a sharper disk as the stars approach one another before retreating again to a more distant spark. This double arrangement imposes strict rules on where planets can remain over long spans. Close to each star, gravity is simple. A small planet that hugs one sun in a tight orbit feels that star as the dominant pull and can trace a nearly circular path, much as Earth does around the sun. Farther out, the tug of the companion begins to compete and paths become unstable. Calculations show two main families of safe orbits. In one family, planets remain so close to a single star that the other might as well be a bright object in the sky, important for light but not for gravity. In the other family, planets orbit far enough out that they circle both stars together, moving around the pair as if it were a single heavy body. Between those regimes lies a broad chaotic region where small disturbances accumulate. Orbits there tend to become stretched and twisted until over many thousands or millions of years, planets are either thrown outward into the wider system or fall inward to more stable paths. This structure narrows the zone where an Earth-like climate could exist. Around the Sun, the habitable region where liquid water can remain on a rocky surface occupies a generous band of distances. Around one member of a binary, that band must fit inside the inner stable shell of orbits close to the star. Any potentially habitable planet around Alpha Centauri A or Alpha Centauri B would therefore be confined to a relatively tight path, one that keeps it securely held by a single sun, while a second sun rises and sets as an enormous wandering star. The third member of the system, Proxima Centauri, adds a more distant layer. Proxima is a small red dwarf whose mass is only a small fraction of the Sun's. Its light is so faint that from near Alpha Centauri A or B, it would not resemble a sun at all, but a dim, reddish star lost among many others. Its orbit around the central pair is vast, measured in thousands of times the distance between Earth and the Sun. One revolution likely takes hundreds of thousands of years. For a long time, it was unclear whether Proxima is truly bound to the system or only passing nearby, but precise measurements of its motion now indicate that it shares the same overall path through the galaxy as the brighter pair. The gravitational bond is weak yet real, turning the nearest star beyond the Sun into the outer member of a triple system. In this configuration, Alpha Centauri becomes a local laboratory for stellar architecture. At its center, two sun-like stars follow a slow, eccentric dance, carving out narrow corridors where planets might remain for billions of years. Far out, a faint red companion wanders on the edge, carrying at least one known planet pressed very close to its surface. To observers in the solar system, all of this complexity collapses into a single bright point. Only with patient measurement does the island resolve into three suns, whose motions silently dictate where stable worlds can exist and how their skies would look under the blended light of more than one star. A faint red star drifts on the edge of the Alpha Centauri family, almost invisible from Earth without instruments, yet destined to become the most significant of the three. Long before its nature is understood, careful observers notice something peculiar in the crowded southern sky. Among the countless points of light near the constellations of the Centaur and the Southern Cross, one star moves in step with the bright pair of Alpha Centauri A and Alpha Centauri B. Against the more distant background, the pattern of the sky barely changes over human lifetimes, but precise photographic plates taken years apart reveal that this tiny ember shares almost exactly the same slow crawl as the brighter suns. It is this shared motion, known as proper motion, that first marks the faint object as a potential companion, rather than a random star passing through the field. In the early 20th century, when long baseline measurements of stellar positions begin to accumulate, this inconspicuous point of light stands out. It does not sit still. It glides across the photographic glass in lockstep with Alpha Centauri, hinting that it lies at a similar distance. When its parallax is finally measured, the result settles the matter. This red dwarf resides slightly closer to the Sun than Alpha Centauri A and Alpha Centauri B, nudging the title of nearest known star away from the bright pair and onto this almost invisible neighbor. In recognition of that special status, it receives a name that fixes its role, Proxima Centauri, the nearest of Centaurus. On any map of the solar neighborhood, Proxima Centauri occupies a position that seems almost intimate. Yet the physical nature of the star is the opposite of grand. Proxima Centauri is a red dwarf of very low mass, hovering just above the threshold at which hydrogen fusion can continue. Its mass reaches only a small fraction of the mass of the Sun, and its radius is not much larger than that of the planet Jupiter. The surface temperature of this miniature star is only around 3000 degrees on the Kelvin scale, barely more than half the temperature of the Sun, so its light emerges in a deep red and infrared glow. In total power output, Proxima Centauri shines with less than 1/5 of 1% of the luminosity of the Sun, and in visible wavelengths, it is dimmer still. Under realistic circumstances, it could never have been noticed as a naked eye star from Earth at its actual distance. Only the patient work of telescopes and repeated imaging brings it into awareness. As measurements refine, astronomers work to determine whether this ultra-faint ember is truly gravitationally bound to Alpha Centauri A and Alpha Centauri B, or whether it merely shares a similar path through space by coincidence. The separation is enormous. Proxima Centauri lies tens of thousands of astronomical units away from the central pair so far that the light from Alpha Centauri A and Alpha Centauri B would take months to cross the gap. At such distances, the gravitational bond is fragile. Passing stars and the tidal field of the galaxy continually tug at the system, threatening over long timescales to peel the outer member away. For decades, the answer remains uncertain. Gradually, as radial velocities and three-dimensional motions are measured with increasing precision, a clearer picture emerges. The small star and the bright pair share not only position on the sky, but a common movement through space. Their velocities are so closely matched that the probability of an accidental alignment becomes very small. The most consistent interpretation is that Proxima Centauri moves in a vast elongated orbit around Alpha Centauri A and Alpha Centauri B, with a period that likely spans hundreds of thousands of years. In that slow circuit, Proxima acts as a distant sentinel on the edge of the nearest stellar system. Its path probably carries it through regions filled with comets and minor bodies, stirring their distribution with each passage and reshaping the outer architecture of the system, much as the Sun perturbs its own cloud of distant icy objects. From the perspective of an observer near Alpha Centauri, a Proxima Centauri would not look like a sun at all. It would appear as a faint reddish star, lost among many others, noticeable only with careful charts. Yet from the perspective of the wider cosmos, this unremarkable dwarf becomes the nearest star of all. Its low mass grants it an extraordinary lifespan. While the Sun will exhaust its core hydrogen in about 10 billion years, a star like Proxima Centauri can burn for trillions of years, slowly converting its fuel in a deep red, steady glow, long after larger stars have faded. In the far future of the galaxy, when many luminous suns have swollen and vanished, red dwarfs like Proxima will dominate the remaining starlight. This contrast between apparent insignificance and cosmic endurance gives the nearest star a peculiar character. It is small, dim, and hard to see, yet almost unimaginably long-lived. It orbits its bright companions on so wide a path that no human era will ever witness a full revolution, yet it remains gravitationally attached in a slow dance that outlasts the evolution of planets and possibly of life around all three members. When humanity looks outward from the solar system, therefore, the nearest beacon is not a familiar sun-like twin, but this tiny crimson ember whose fragile light barely reaches the threshold of vision, a quiet marker of how even the closest destination can be at once almost within reach and profoundly remote in both distance and time. Around the dim ember of Proxima Centauri, attention gradually shifts from the star itself to the possibility that something might be circling close to its weak red light. For many years, red dwarfs receive little consideration as potential hosts of interesting worlds. Their faintness makes precise observations difficult, and their reputation as restless, flaring stars suggests hostile environments. Yet their very abundance in the galaxy, combined with the long lifetimes promised by their slow fusion, draws curiosity back to them. Proxima Centauri, being the nearest of all, becomes an obvious target for patient, careful scrutiny. At observatories in the southern hemisphere, high-precision spectrographs are turned toward this almost invisible neighbor. Night after night, year after year, they collect its light and spread it into detailed spectra, delicate rainbows, crossed with dark lines, where atoms in the stellar atmosphere absorb specific colors. These absorption lines serve as markers, fixed reference points that shift slightly when the star moves toward or away from the observer. If a planet orbits Proxima Centauri, both star and planet must circle a common center of mass. The planet follows a wide path, the star a tiny mirrored loop. To an observer aligned roughly along that motion, the star periodically drifts a little closer and then a little farther, its light minutely compressed and stretched. The effect on the spectrum is almost unimaginably small. The dark lines slide back and forth by fractions of a pixel on the detector, corresponding to changes in speed comparable to a relaxed walking pace. Isolating such a signal from the noise of the star's own activity and from instrumental imperfections demands patience and statistical care. Gradually, a pattern emerges. Measurements taken over many months reveal a regular oscillation in the velocity of Proxima Centauri along the line of sight. The star approaches slightly, then recedes in a cycle that repeats with clock-like regularity, approximately every 11 days. The amplitude of this motion is tiny, only a few meters per second, yet the repeating pattern stands out against the random flares and jitter. Through the language of gravity, this gentle rocking points to an unseen companion. By combining the period of the wobble with its amplitude and the known mass of the star, astronomers can infer the minimum mass of the object that is causing it. The solution indicates a world at least slightly more massive than Earth, orbiting extremely close to the red dwarf. The planet received the designation Proxima Centauri b, marking it as the first detected world around the nearest star. From the perspective of orbital mechanics, Proxima Centauri b moves on a very tight leash. Its orbit lies at a distance of only about 7.5 million kilometers from the star, a span that in the solar system would place it far inside the orbit of Mercury. In that close embrace, 1 year for the planet lasts only a little more than 11 Earth days. The world rushes around its star so rapidly that its sky would change noticeably over the course of an ordinary human week if an observer could stand on its surface and watch. Despite this proximity, Proxima Centauri b does not necessarily bake under intolerable heat. The faint nature of its host star shifts the usual intuition. Proxima Centauri radiates so little energy that its habitable region, where a planet might receive the right amount of warmth to permit liquid water is squeezed inward until it hugs the star like a narrow ring. Calculations suggest that this ring extends roughly from just over 4/100ths to a little more than 8/100ths of the distance between Earth and the Sun. The orbit inferred for Proxima Centauri b falls neatly inside this slender band. As a result, the simple temperature-based definition places the nearest known exoplanet of roughly Earth mass squarely within the so-called habitable zone of the nearest star beyond the Sun. That combination of properties captures immediate attention. The nearest stellar neighbor hosts a world that is not a gas giant, not a bloated hot planet larger than Neptune, but a compact, likely rocky sphere, only a little heavier than Earth, receiving a level of starlight not dramatically different from that which bathes the home world of humanity. On paper, it looks almost ideal, as if the cosmos had placed the first step toward other suns just beyond the boundary of the solar system. The discovery triggers a wave of modeling efforts. With only a minimum mass and an orbital period in hand, researchers attempt to reconstruct the possible surface conditions of this small planet in the red glow. They explore scenarios in which Proxima Centauri b holds a thick atmosphere rich in greenhouse gases, or a thinner one more similar to that of Earth. They consider the impact of clouds, of oceans, of continents, of various degrees of reflectivity. In their simulations, the equilibrium temperature of the planet hovers near values that, with the right atmospheric blanket, could keep water in a liquid state on the surface. In some cases, the planet becomes a warm, globally oceanic world. In others, it is locked in ice with only a narrow band of possible liquid water near the terminator. In still others, it is a steam-shrouded sphere swaddled in thick clouds. Each variation depends on initial assumptions that cannot yet be checked by direct observation. At the same time, the very closeness that makes Proxima Centauri b temperate in principle introduces other, more unsettling consequences. Tidal forces from the star likely long ago synchronized the planet's rotation with its orbital period. In that case, one hemisphere would face Proxima Centauri at all times, experiencing a slow, never-ending day under a dim red sun that hangs motionless in the sky, while the opposite hemisphere remains locked in permanent night. Heat transport by any atmosphere or ocean would govern whether the day side becomes a scorched desert and the night side a frozen vacuum, or whether a more moderate band of conditions emerges along the twilight ring. The same proximity that carries the planet into the habitable zone also buries it deep inside the star's magnetic environment, subjecting it to winds and flares whose true impact is only beginning to be understood. For a brief moment, however, before those complications are fully explored, Proxima Centauri b holds a special kind of allure. It is the first known world of near-Earth mass in the temperate zone of the nearest star, a concrete and specific target where previously there was only the abstract idea of other planets in other systems. In the quiet hours after the announcement of its detection, the imagination lingers on a small dark world circling in less than a dozen days around a crimson sun, its surface perhaps rugged and bare, perhaps hidden under clouds, perhaps home only to rock and ice, but undeniably there, orbiting within reach of future instruments and serving as the first solid stepping stone in the long consideration of what it would mean to travel one day beyond the boundary of the solar system toward an actual place and not only toward a point of light. The phrase habitable zone enters the story of Proxima Centauri b as a deceptively simple promise. In diagrams, it appears as a soft ring around a star, a band of distances where the warmth from that star allows liquid water to exist on the surface of a rocky world. Around a sun-like star, this band is comfortable and broad. Inside it, surface ice can melt melt into oceans. Outside it, those oceans either boil away or freeze solid. It is an appealing picture because it compresses the complex question of habitability into a single measure, the distance from the parent star. Against this backdrop, the discovery of Proxima Centauri b is first framed in the same language. Proxima Centauri emits only a small fraction of the energy of the Sun, so the zone where a planet can balance between ice and steam clings close to the stellar surface. The equations that define the classical habitable zone take into account the luminosity of the star and the way light thins with distance. Applied to Proxima Centauri, they place both the inner and outer edges of the temperate band very near the star. Within this narrow annulus, a planet with a reasonably thick atmosphere can in principle maintain liquid water on its surface. When the orbit of Proxima Centauri b is overlaid on this model, its path falls neatly inside the ring. On paper, the nearest exoplanet of near-Earth mass lies in the heart of its star's habitable zone. The nearest star beyond the Sun appears to host not only a rocky planet but one placed in the most promising range of orbits. Yet as attention lingers on this clean overlap, the limitations of the concept begin to show. The original idea of a habitable zone is based on a simplified planet and a gentle star. It assumes a world with an atmosphere that can be described by a few average numbers, and a star whose output is stable and calm. Around a star like the Sun, this is a reasonable first approximation. Around a red dwarf like Proxima Centauri, the same assumption becomes fragile. The star's luminosity is low, which pushes the habitable zone inward until it hugs the star in a tight ring. That inward shift means that any planet in the classical temperate band is not merely near its star, it is buried deep inside the star's magnetic and particle environment. The habitable zone becomes a thin shoreline, washed not only by light, but by winds of charged particles and sudden bursts of high-energy radiation. Distance alone no longer captures the difference between a benign orbit and a hostile one. Even if the star were perfectly steady, temperature is more subtle than the simple diagram suggests. The amount of energy that reaches the top of a planet's atmosphere is only the first step. How that energy is absorbed, reflected, and spread around the globe depends on atmospheric composition, cloud cover, surface type, and rotation. On a tidally locked world, like Proxima Centauri b, where the same hemisphere always faces the star, the balance between light and darkness is extreme. The day side receives constant illumination, the night side almost none. In a simple climate model with a thin atmosphere, the illuminated hemisphere heats up while the dark side cools towards space. In such a case, the habitable zone might fail in practice. Atmospheric gases could condense and freeze on the night side, slowly draining the air from the day side until little remains but a vacuum and an ice cap of frozen atmosphere. More sophisticated models introduce a denser atmosphere and perhaps an ocean. In those simulations, winds and currents driven by the temperature contrast between day and night, transport heat toward the terminator, the permanent band of twilight that encircles the planet. Under the right conditions, a region of the surface can settle into intermediate temperatures, neither boiling nor frozen. In some scenarios, the planet takes on a so-called eyeball state, with a warm, possibly oceanic area centered on the substellar point, surrounded by a ring of ice flowing into the frozen night side. In others, cloud decks build over the hottest regions and reflect part of the incoming light, acting as a natural thermostat. Each of these possibilities sits within the classical habitable zone, yet the actual experience at the surface differs strongly. The same star, the same total energy, and the same orbital distance can produce a lifeless rock, a world with scattered pockets of marginal habitability, or a comparatively mild planet with liquid water in selected regions. The phrase habitable zone, when applied to Proxima Centauri b, therefore becomes less a guarantee and more a starting point. It marks only those orbits where energy budgets make liquid water possible in principle. It says nothing about whether an atmosphere has survived, about the violence of stellar flares, about magnetic fields, or chemical histories. As the nearest red dwarf planet, Proxima Centauri b illustrates this limitation sharply. Its presence in the temperate ring raises hopes, and the mathematics of the habitable zone draws a clear and inviting diagram. Yet the details of its environment suggest that habitability is a fragile dependent property that rests on a stack of conditions, many of which remain unknown. In that sense, the narrow belt around Proxima Centauri is both an anchor and an illusion, a ring that focuses attention while at the same time reminding observers that distance from a star is only the outermost layer of a far more intricate question. On Proxima Centauri b, gravity and time together carve the planet into two permanent hemispheres, one endlessly bathed in the ruddy light of its star and the other buried in unbroken night. The root of this division lies in tidal locking, a phenomenon that arises whenever a massive body holds a smaller companion in a close orbit for long enough. Proxima Centauri b circles its star in a little more than 11 Earth days at a distance of only a few million kilometers. At that range, the near side of the planet feels a slightly stronger gravitational pull than the far side. Over many millions of years, this difference acts as a brake on rotation, converting rotational energy into heat within the planet's interior. The process gradually slows and reshapes the spin until one hemisphere always faces the star, just as the same face of the moon is always turned toward Earth. Once this synchronous state is reached, the dynamics freeze into a new rigid geometry. On the dayside hemisphere, a single point becomes special. This is the substellar point, the location where Proxima Centauri stands directly overhead at all times. There, the red dwarf never rises or sets. It hangs at the zenith in a fixed position across ages, casting light and energy straight down. Moving away from this point in any direction lowers the star toward the horizon. Along great arcs across the surface, the star remains forever at the same angle, a dim ember higher or lower in the sky, depending on latitude and longitude. Eventually, a line is reached where Proxima Centauri skims the horizon, neither rising nor sinking. This great circle marks the terminator, the boundary between the everlasting day and the everlasting night. Beyond it lies the night side, a hemisphere that never receives direct starlight, illuminated only by faint reflections, background stars, and perhaps a distant glimmer from Alpha Centauri A and Alpha Centauri B. Climate on such a world cannot be described by a single global average. At the substellar point, energy arrives constantly without the relief of sunset. Even though Proxima Centauri is faint compared to the Sun, the continuous exposure concentrates heat in this region. If Proxima Centauri b possessed no atmosphere, the dayside surface under the fixed star would likely rise to temperatures high enough to melt rock in places, while the night side would radiate its internal warmth away into space until it reached extremely low temperatures, perhaps only a handful of degrees above absolute zero. The planet would resemble a sphere split between a scorched hemisphere and a deep frozen hemisphere, a stark world of fire and ice. The presence of an atmosphere alters this picture. Gas in motion can redistribute energy, softening the contrast between day and night. In thin atmospheres, the effect is modest. Winds carry some heat from the illuminated hemisphere toward the dark side, but as air cools, it can condense and freeze onto the surface. Over long timescales, this process can lead to atmospheric collapse. Volatile gases accumulate as frost on the night side, slowly depleting the atmosphere above the day side, until the remaining envelope becomes too thin to circulate effectively. Proxima Centauri b in this scenario ends as a nearly airless world with a permanent cap of frozen gases coating the dark hemisphere, while the illuminated side bakes under direct radiation without protection. In thicker atmospheres, the story unfolds differently. When the air column above the surface is dense, heat capacity grows. Warm air near the substellar point rises and flows toward cooler regions, while cooler air from the night side moves in to replace it. This circulation can form persistent jet streams and vortices that carry heat across the terminator. In numerical models that explore such conditions, a variety of exotic climate states emerge. In some solutions, the planet stabilizes into an eyeball configuration, with a roughly circular region of relatively warm temperatures centered on the substellar point, surrounded by a broad ring of ice that extends onto the night side. The eye appears as a liquid or partially liquid patch on a mostly frozen planet, sustained by constant illumination and buffered by atmospheric transport. In other solutions, reflective cloud decks form over the hottest regions. As water vapor or other condensable substances rise in the intense updrafts near the substellar point, they cool and condense into thick clouds. These bright layers act as mirrors, sending a significant portion of the incoming light back into space. This natural shielding moderates surface temperatures beneath and expands the area where conditions could remain between freezing and boiling. The terminator becomes a band of perpetual twilight where temperatures and illumination are intermediate. Along this great circle, the star sits fixed on the horizon, casting a permanent sunrise or sunset glow across any landscape that might exist there. If liquid water is present and an atmosphere survives, this region could harbor the most stable conditions, with modest winds, soft light, and temperatures that change little over time. Inhabitability in that case would be confined not to an entire globe, but to a ring, a thin habitable belt wrapped around a planet of extremes. All of these outcomes depend sensitively on properties that remain unknown. The mass and composition of Proxima Centauri b allow for a rocky planet, but they do not reveal its inventory of water or gases. The strength of any magnetic field is also uncertain. A global magnetic shield can deflect some of the charged particles streaming from Proxima Centauri and reduce the erosion of the atmosphere by stellar wind and flares. Without such protection, high-energy particles and radiation can strip gases more efficiently, driving the planet toward the airless, collapsed scenario, even if it once possessed a thick atmosphere. The star's behavior complicates matters further. Proxima Centauri is known to flare, frequently unleashing bursts of ultraviolet and X-ray radiation. Each flare heats and expands the upper atmosphere of the planet, if any remains, enhancing the escape of light gases into space. Over billions of years, this repeated pulsing of energy can remove entire oceans' worth of volatiles. The classical label of habitable zone, when placed on such a system, must therefore be read as a purely geometric and energetic description. Proxima Centauri b sits at a distance where, with a suitable atmosphere and surface, liquid water could exist somewhere on the planet. Whether any part of the surface actually enjoys such conditions depends on the history of that atmosphere in the face of tides, winds, and flares. The tidally locked geometry ensures that any surviving habitability would be sharply structured in space, focused into a region on or near the day-night boundary. As the nearest terrestrial exoplanet in a nominally temperate orbit, Proxima Centauri b becomes a prototype for this class of worlds, showing how unfolds into a layered reality where day and night are not cycles but fixed hemispheres, and where climate is sculpted by the delicate interplay between a dim active star and the thin shell of gases that may or may not still cling to the rock that circles it. Proxima Centauri, small and dim in total light, reveals a different kind of intensity when its magnetic heart is examined more closely, because the same low mass that keeps its fusions low also makes its interior almost entirely convective, with hot plasma rising and sinking from core to surface in a constant boil that twists and stretches magnetic fields until they knot upon themselves. In a star like the Sun, layers separate regions of convection and radiation, smoothing some of this turmoil and confining the strongest magnetic activity to certain belts. But in Proxima Centauri, the churning extends throughout, nearly the whole volume, building tangled magnetic structures that store energy for long periods before releasing it in sudden bursts. These releases take the form of stellar flares, explosive events, in which reconfiguring magnetic fields hurl charged particles outward and flood surrounding space with a surge of radiation across the spectrum. For a red dwarf, flares are not rare accidents. They are woven into the normal pattern of behavior. Proxima Centauri exhibits small flares so frequently that its brightness, if tracked in detail, pulses like a restless heartbeat. Against this background of minor flashes, larger events occasionally stand out: super flares, in which the star abruptly brightens by large factors in ultraviolet and X-ray wavelengths. In a short span of minutes, the output in these energies can rise by orders of magnitude before subsiding again. For a distant observer, these events are measurements and graphs, spikes on a screen. For any planet orbiting close to the star, they are environmental shocks that reshape the meaning of habitability. Proxima Centauri b, circling in only a little more than 11 Earth days, at a distance of a few million kilometers, occupies a position where the classical habitable zone overlaps almost exactly with the region of strongest magnetic influence and particle wind. The planet does not sit at the edge of a gentle radiative glow. It hovers near the surface of an unruly magnetic engine. Between flares, a steady stream of charged particles flows outward as stellar wind, a river of ionized gas that presses persistently on any planetary magnetic field and erodes the outer layers of any atmosphere that reach high altitudes. When a flare erupts, that steady pressure spikes. Waves of energetic protons and electrons race outward, accompanied by disturbances that accelerate particles farther still. At the same time, the star's output in high-energy photons climbs dramatically. Ultraviolet light and X-rays pour into interplanetary space in quantities that dwarf their usual levels. On Proxima Centauri b, the upper atmosphere, if one exists, absorbs much of this radiation. Molecules and atoms there are ionized and heated, their electrons stripped away, their motions accelerated into a state that is more like a thin plasma than a calm gas. With enough energy, some of these particles reach speeds that exceed the escape velocity of the planet and stream away along open magnetic field lines or simply evaporate into space. Each flare therefore acts as a brief, intense pulse of atmospheric loss. Over timescales of days or years, individual events might not remove much mass, but Proxima Centauri does not flare once per century. It flares frequently, often, and sometimes violently. Over hundreds of millions and then billions of years, this rhythmic beating of radiation and wind can strip away entire oceans worth of water vapor and huge fractions of an atmosphere's original content. The surface environment under such a sky depends critically on shielding. On Earth, a combination of the global magnetic field and a substantial atmosphere guards the biosphere from most harmful high-energy radiation. The magnetosphere deflects many charged particles, steering them into belts and auroras, near the poles, while the air itself absorbs the majority of ultraviolet and X-ray photons before they reach the ground. This layered protection allows life to exist without constant exposure to lethal doses of radiation. For Proxima Centauri b, the situation is less forgiving. If the planet lacks a strong magnetic field, perhaps because tidal locking has slowed its rotation and altered the conditions in its core, its atmosphere faces the full brunt of the stellar wind. Charged particles spiral into the upper layers of gas, depositing energy and driving escape. Without a substantial atmosphere, the remaining surface, if solid, lies nearly bare to high-energy photons that can penetrate rocks to shallow depths. Even microbes buried beneath the ground must endure a long, cumulative exposure. If the planet does retain a magnetic field, some shielding is possible, but the close orbit means that the magnetosphere is compressed by the dense wind, pushed inward until it clings tightly to the planet. In that compressed configuration, strong flares can still inject large amounts of energy into the atmospheric shell. For life as chemistry, the consequences are severe. Complex organic molecules, including those that might encode genetic information, are fragile under intense ultraviolet and X-ray bombardment. Bonds break, structures unravel, and replication, if it begins at all, is hampered by a constant backwash of damage. Some scenarios imagine life retreating into subsurface environments, perhaps in oceans under rock or ice, where the overlying material acts as a shield. Others suggest that even those refuges might be compromised over very long times if the atmosphere and surface water are largely removed. In that view, Proxima Centauri b becomes a monument to lost possibilities, a world that may have started with water and air, only to lose them gradually to its own star's restlessness. From a distance, the orbit of the planet remains exactly where the habitable zone calculation places it. In diagrams, Proxima Centauri b continues to glide through the familiar green band that marks a temperate region. The reality that unfolds upon closer inspection is that for red dwarfs of this kind, the habitable zone can coincide with a zone of continuous sterilization and erosion. The same closeness that provides the right average warmth also guarantees immersion in a storm of high-energy light and charged particles that slowly removes the conditions required for surface water and a stable atmosphere. Proxima Centauri, in this sense, burns its own shoreline, bathing the region where a calm, mild world could exist in a fluctuating radiative surf that steadily grinds down any fragile envelope of air and water that a small rocky planet might once have possessed. On Proxima Centauri b, the story of air and water becomes a slow unraveling, stretched across billions of years, driven not by a single catastrophe, but by countless small losses that accumulate until an entire atmosphere and ocean budget can be transformed or removed. At the beginning, in many formation scenarios, the planet does not look unusual. It condenses from the same protoplanetary disk that forms Proxima Centauri itself, gathering rock metals and volatile ices. If it forms beyond the inner hot regions and later migrates inward, or if icy bodies fall onto it from farther out, it can accumulate water in amounts comparable to those of Earth or greater. Early on, a young Proxima Centauri b may host a deep global ocean beneath a sky rich in gases, released by volcanism impacts and outgassing. In this early epoch, the red dwarf is more active than in its mature state. High-energy radiation and stellar winds are stronger and flares erupt with ferocity. The newborn planet endures a phase of intense bombardment not only by residual debris from formation, but also by the particle and photon storms from its star. Under such a sky, the upper layers of the atmosphere absorb enormous quantities of ultraviolet and X-ray light. Molecules of water and carbon dioxide split into their components. This process called photodissociation breaks each water molecule into hydrogen and oxygen. The light hydrogen atoms, once freed, are easily accelerated to speeds above the escape velocity of the planet, especially when the upper atmosphere is heated and expands to many times its original thickness. In that extended state, hydrogen drifts away along magnetic field lines or leaks from the exosphere into space. Over time, this escape acts like a slow leak in a reservoir. Ocean molecules rise as vapor sunlight tears them apart, and the lightest fraction vanishes into interplanetary space. If the supply of water is not replenished, a world that begins with deep oceans can lose much of its inventory over hundreds of millions of years. The heavier oxygen left behind does not escape as easily. Instead, it accumulates in the atmosphere or reacts with the surface. On a geologically active planet, oxygen combines with iron and other elements in rocks, oxidizing them and driving the color of soils and basalts toward deeper reds and browns. If outgassing from the interior continues to supply reduced gases that consume oxygen, a balance may be maintained. If not, the atmosphere can, at least for a time, become enriched in oxygen even in the absence of life. What looks like a respiratory signature of biology could in some cases be the silent echo of oceans lost long ago. Meanwhile, the escape of gas is not limited to hydrogen. Energetic particles from Proxima Centauri, guided by magnetic fields, slam into the upper atmosphere and knock heavier atoms and molecules to escape speeds. This process, known as sputtering, chips away at the outer layers of the gaseous envelope, like a constant microscopic sandblasting. When strong flares heat the ionosphere, they can also drive bulk flows of ionized gas outward in what amounts to atmospheric evaporation. Proxima Centauri b, subject to a dense wind and high radiation flux at very close distance, faces these processes in an amplified form. Whether any atmosphere survives the full fury of billions of years under Proxima Centauri depends on a competition between sources and sinks. Volcanic eruptions, tectonic recycling and cometary impacts can add gases, while escape chemical weathering and sequestration into rocks remove them. Models that attempt to follow this balance under realistic flare histories often arrive at sobering conclusions. Even if Proxima Centauri b begins with an atmosphere as thick as that of Earth or Venus and oceans many kilometers deep, the integrated effect of constant flaring and wind pressure can, over billions of years, strip away most of the volatile layer unless shielding is unusually strong. The end state of such an evolution is a planet that has been dried and skinned. Any former oceans exist only as hydrated minerals in the crust or as thin deposits of ice in permanently shadowed craters on the night side. The atmosphere, if any persists, may be a tenuous veil dominated by heavier gases at pressures too low to support stable surface liquid water. The surface itself, bombarded for eons by high-energy particles and radiation, becomes chemically altered, its upper layers darkened or reddened by complex carbon chemistry and repeated oxidation. In this picture, Proxima Centauri b transforms from a potentially oceanic world in its youth into a dry, air-poor rock. In maturity, its habitability eroded not by a single disaster, but by the very environment that placed it in the classical habitable zone. Yet, this trajectory, while likely, is not absolutely fixed. A powerful magnetic field could reduce escape rates. An unusually massive initial water inventory could leave residual oceans even after extensive loss. Subsurface reservoirs might harbor liquid water beneath insulating rock and ice decoupled from the hostile surface. The key point is that around a star like Proxima Centauri, the fate of air and water is inseparable from stellar activity. To understand whether the nearest terrestrial exoplanet is a bare stone or a world that still clings to some of its primordial envelope, observers must not only measure its mass and orbit, but also decipher the long flickering history of the red dwarf that has shone upon it since its formation. A history written in flares, winds, and the slow escape of atoms into the darkness between the stars. The gradual realization that Proxima Centauri b is almost certainly a harsh and stripped world shifts attention back toward the space between stars itself and toward the tools that might one day attempt to cross it, revealing that the main barrier is not simply distance, but the way propulsion works at a fundamental level, a barrier that is expressed compactly in what is known as the rocket equation. Every spacecraft launched from Earth so far has relied on the same basic principle. A rocket carries a store of propellant, expels part of its own mass backward at high speed, and in response moves forward. The faster the exhaust is thrown out the back, the more efficiently the rocket gains speed. This connection between exhaust speed and performance appears in the notion of specific impulse, which measures how much thrust is obtained from a given amount of propellant. Chemical propellants, which release energy by rearranging the bonds between atoms in molecules, reach exhaust speeds of only a few kilometers per second. Even the most advanced combinations of liquid hydrogen and liquid oxygen produce exhaust velocities of only a few times 10 kilometers per second. These numbers are impressive when measured against human motion, yet the gulf to the nearest star requires much more. The rocket equation, derived by Konstantin Tsiolkovsky in the early 20th century, links three essential quantities. The change in velocity a rocket can achieve depends on the exhaust speed of its propellant and on the ratio between the initial mass of the rocket fully fueled and the final mass after the fuel is expended. The relationship is logarithmic. Doubling the change in velocity does not simply double the mass of fuel required. It demands an exponential increase. This logarithmic form gives the equation its reputation as a tyranny, because it makes high speeds disproportionately expensive in propellant mass. Within the solar system, this tyranny is manageable. To reach low Earth orbit, a rocket must add roughly 8 kilometers per second to its speed. To escape Earth and travel to Mars or Jupiter, a little more is needed. Multi-stage rockets and gravitational assist can supply the necessary increments. The mass ratios involved are large, but not impossible. Launch vehicles burn through most of their mass, as propellant leaving only a small fraction as payload and empty structure, yet that fraction suffices to carry instruments, landers, and the occasional crew. When this same framework is extended to interstellar travel, the numbers begin to distort into extremes. A spacecraft leaving the solar system at a speed similar to that of Voyager 1, on the order of 17 kilometers per second, still requires tens of thousands of years to reach Proxima Centauri. To reduce that travel time to something closer to a human lifetime, say a few tens of years, the cruise speed must increase by 3 orders of magnitude to a significant fraction of the speed of light. If one imagines a purely chemical rocket attempting such a feat, the rocket equation quickly reveals the scale of the impossible. With an exhaust speed of perhaps 4 or 5 kilometers per second, achieving a final speed, even of 100 kilometers per second, would already demand a mass ratio so extreme that almost the entire launch mass would need to be propellant. Pushing into thousands or tens of thousands of kilometers per second multiplies this requirement until the mass of propellant needed to accelerate a modest spacecraft becomes comparable to or greater than the mass of entire planets. Even before engineering enters the discussion, the mathematics alone indicates that chemical energy as stored in molecular bonds is insufficient. There is simply not enough energy per unit mass to push a significant payload to interstellar speeds without invoking absurd quantities of propellant. Attempts to bypass this barrier using gravity assists, as Voyager did face their own limitations. Within a planetary system, a spacecraft can steal tiny amounts of orbital energy from giant planets by swinging past them in carefully planned trajectories. Each pass changes the spacecraft's speed relative to the Sun without expending additional propellant. However, once the outer planets have been used, there are no more gravitational stepping stones. Beyond the orbit of Neptune, the spacecraft enters interstellar space, where stars lie far apart, and no convenient massive bodies are available for repeated slingshots. Whatever speed the spacecraft carries at that point is essentially the speed with which it must traverse the entire gap between stars. The tyranny of the rocket equation applies not only to the initial acceleration, but also to any attempt to slow down at the destination. To enter orbit around Proxima Centauri or its planet, a spacecraft must shed almost as much velocity as it gained leaving the solar system. If it intends to decelerate using its own engines, it must carry additional propellant for braking. The rocket equation then compounds the problem. Propellant carried for deceleration must itself be accelerated at departure, which means carrying even more fuel to push that fuel, and so on. The mass of propellant grows in layers, each layer added to move the ones above it, until in a purely chemical design, the total mass expands beyond practical or even conceivable limits. This realization gradually reframes the 75,000-year travel time of a Voyager-like probe, not as a result of human caution or engineering conservatism, but as a direct consequence of fundamental physics. Within the constraints of chemical energy and expelling propellant, there is no reasonable path to interstellar flight on human timescales. To change the situation, the terms of the equation must be altered either by increasing exhaust velocities, through more energetic reactions, such as nuclear processes, by reducing the need to carry propellant at all through external propulsion, or by accepting very long voyage durations and designing missions that can survive them. Alpha Centauri and Proxima Centauri thus serve as calibration points. The known speed of existing spacecraft, the energy content of chemical bonds, and the unyielding logarithm in the rocket equation combine to show with quiet clarity that the methods which have carried probes to the outer planets are fundamentally local tools. They are well suited to crossing the internal pond of the solar system, but when applied to the ocean between stars, they become almost motionless. The nearest stellar neighbor remains on the map only 4 light-years away, yet in terms of energy and propellant, it might as well reside behind a wall that chemical fire alone cannot breach. Arcs in the long night emerge as an idea when the limits of propulsion become too rigid to bend. If engines cannot make the journey to Alpha Centauri short, the journey itself must change shape. Time rather than speed becomes the adjustable quantity. Instead of a crossing completed within a single lifetime, theorists imagine a ship that is itself a world, a closed environment designed to persist for many thousands of years while it drifts between stars. In this concept, the vessel is not simply a vehicle. It is the only home its inhabitants ever know. Generations are born, live and die within its walls, while the original destination recedes into legend, and the point of departure becomes prehistory. Such a ship must be an ark in more than name. It must enclose an entire biosphere, miniature yet complete. Air, water, and nutrients cannot be wasted. Every atom that passes through lungs, roots, or circuits must be captured and recirculated. Life support becomes an artificial ecology. A generation ship would have to function for spans comparable to recorded human history, without resupply and with only self-repair. On the scale required, hydroponic farms and algae tanks become quiet fields and reservoirs stretching through the interior. Artificial lighting mimics a day-night rhythm, even though the stars outside no longer provide a meaningful cycle. Waste returns as fertilizer water is purified and reissued. Trace elements are restored from stockpiles. Small inefficiencies negligible over months become dangerous when extended across thousands of years. A slow drift in atmospheric composition or the spread of a single organism could over centuries push the closed system toward collapse. Designing such an environment is not just assembling machines but crafting a resilient micro-world that can absorb shocks and settle into new equilibria. Beyond ecology lies genetics. A population confined to a finite volume for many generations faces the risks of inbreeding and genetic drift. To maintain health and diversity, the founding population cannot be small. Studies of isolated communities suggest that thousands of unrelated individuals may be required to avoid an accumulation of harmful traits. Alternatively, frozen banks of embryos, sperm and eggs could be stored, providing a reservoir of diversity that can be introduced gradually. Part of the ark becomes a genetic archive, encoded in cryogenic vaults that must remain stable and powered for millennia. The social structure inside such a vessel presents a different difficulty. At launch, a clear mission exists. The ark leaves the solar system bound for Alpha Centauri. Its purpose is defined by the will of those who design and fund it. A few generations later, that clarity may have softened. For descendants born in transit, the mission is not a project but a background story. There is no living memory of open sky or of the world that launched the ship. Daily reality is corridors, gardens under lamps, and the hum of systems that must never stop. Maintaining the knowledge required to operate and repair the ark becomes a central challenge. Technologies degrade if understanding of their function is lost. Manuals and databases can preserve instructions, but literacy and education must be sustained. If they falter, crucial skills may vanish within a few generations. Some designers imagine rigid institutions, perhaps cast as orders or guilds, whose role is to transmit technical expertise and mission history. Others fear that any rigid structure risks stagnation or rebellion. Internal conflicts or ideological schisms could damage key systems or redirect the priorities of the society on board. Alternative concepts attempt to bypass the need for continuous culture by replacing awake generations with sleepers. In the sleeper ship scenario, the ark carries a relatively small number of individuals in suspended animation. They enter a state of deep metabolic slowdown or cryogenic stasis shortly after departure and do not experience the passage of time. For them, a voyage of many thousands of years would feel like a single extended sleep. Robotic caretakers controlled by artificial intelligences maintain the vessel, correct course, manage resources, and oversee the integrity of the sleeper's life support. At the end of the journey, automated procedures revive the crew in orbit around the target system. This vision trades sociological complexity for biological and engineering risk. The mechanisms of long-term suspended animation in complex mammals are not yet understood or controlled. Even if perfected, tiny probabilities of failure for each capsule accumulate over millennia. Unforeseen chemical reactions or slow degradation of materials could compromise the system. The guardians of the sleepers must themselves be robust against hardware failures and radiation-induced errors. The ark becomes a hierarchy of trust. The sleeping population depends entirely on machines that cannot be repaired by conscious hands until the journey is complete. In both generation and sleeper ships, the crossing to Alpha Centauri remains a passage through the long night, a period so extended that ordinary intuitions about planning and responsibility begin to drift. Decisions made at launch bind people who never consented to them, yet must live or sleep inside their consequences. The star that waits at the end of the journey, already known to host a likely barren planet swept by flares, offers little as a refuge. The purpose of such arcs would not be to find a better home, but to demonstrate that a fragile, self-aware species can in principle build a pocket of continuity that stretches across the interstellar gulf. Even when distance is accepted and time is allowed to reach into many thousands of years, the difficulties of ecology, genetics, culture, and reliability combine into a new kind of barrier, one made not of kilometers, but of continuity itself. Riding on nuclear fire begins as an idea when the energy in chemical bonds is finally weighed against the scale of interstellar space and found too small. Within the atom there is a deeper reservoir that releases energy not by moving electrons, but by altering the nuclei themselves. Fission splits heavy atoms into lighter fragments. Fusion presses light atoms together until they merge, and in both cases the yield per unit mass exceeds chemical reactions by factors of millions. If a rocket could be driven directly by nuclear reactions, its exhaust could in principle reach speeds far beyond those of any chemical flame. In the middle of the 20th century, this reasoning takes concrete form in a concept often called a nuclear pulse ship. At its core lies a simple, severe idea. Instead of burning propellant inside a chamber and letting exhaust flow steadily through a nozzle, the ship carries a stock of small nuclear devices and ejects them one by one behind a massive metal plate. Each device detonates at a chosen distance. The expanding fireball slams into the plate, vaporizes a thin outer layer, and drives the whole assembly forward, while a forest of shock absorbers turns each violent jolt into a smoother push. Detonations repeat every second or so, and the ship lurches ahead in a sequence of nuclear kicks that add up to continuous acceleration. Calculations indicate that such a vessel could lift thousands or even millions of tons into space, and then continue accelerating until it reached a significant fraction of the speed of light. Under sustained pulsing, a large craft could, in theory, cruise at perhaps 1/10 of light speed. At that velocity, the journey to Alpha Centauri would shrink from tens of thousands of years to only a few decades, short enough that a crew leaving the solar system in youth could arrive in the same lifetime. The obstacles to this vision are not mainly in its physics. They lie in engineering, environment, and law. To lift a nuclear pulse ship from Earth would require detonating a sequence of nuclear devices in the lower atmosphere, spreading radioactive fallout across the planet. Moving construction into orbit or to the moon would reduce that hazard, but demand an enormous industrial base beyond Earth, and international treaties negotiated in the shadow of nuclear weapons forbid nuclear detonations in the atmosphere and in space. The image of a city-sized ship climbing to the stars on a ladder of nuclear flashes remains a vivid illustration of what fission could do, yet it stays on paper. Where nuclear pulse concepts use many small fission devices, other designs imagine harnessing fusion more directly. In the 1970s, a group within a British interplanetary society studies a fusion-driven probe intended to reach another star within a human lifetime. The design is staged in two main segments. The first stage carries most of the fusion fuel and a large engine. The second, attached ahead, holds a smaller engine and a scientific payload. The fuel consists of tiny pellets of a mixture of deuterium and helium-3. These pellets are fed into a reaction chamber where timed beams compress them until fusion ignites. Each micro-explosion releases hot plasma that magnetic fields guide and expel as exhaust. Repeated many times per second, this process produces a high-velocity jet. In the study, the first stage burns for a little under 2 years, then detaches. The second continues for a similar span, pushing the payload to around 1/8 of the speed of light before shutting down. The craft then coasts the rest of the way. At that cruise speed, a journey to a nearby target star takes a few decades rather than many millennia, though the mission accepts that there will be no braking at the destination. The probe rushes through the target system on a fast flyby, gathering what information it can during a brief passage before sliding onward into deeper dark. The obstacles here are different, but equally deep. Fusion for power on Earth remains an unsolved engineering challenge, and achieving it in a compact repetitive engine suitable for a starship demands advances far beyond current capabilities. The preferred fuel helium-3 is rare on Earth, so in the study, it must be mined in vast quantities from the outer giant planets or from lunar soils, then refined and moved into deep space. The craft itself, with a mass of many tens of thousands of tons, would have to be assembled in orbit and wrapped in shielding against its own radiation. Nuclear pulse ships and fusion arcs therefore occupy a peculiar middle ground in the story of interstellar travel. They are not impossible in the sense that chemical rockets are effectively impossible for the stars. The underlying physics supports them, and their performance on paper reduces the crossing to Alpha Centauri from the span of human history to the span of a human life. Yet they are also not close. They require an industrial and political transformation of the solar system, a civilization willing to handle nuclear devices by the thousand in space, and to devote resources on a planetary scale to a single machine. In that sense, they mark a threshold. If such engines ever become routine, the gulf to the nearest star will have changed character from a barrier that demands 70,000 years of drift to a distance that a single generation can cross. And the idea of a ship riding on nuclear fire toward the 3 suns of the nearest system will move from speculative study toward the edge of practice. Beyond nuclear engines that carry their own fire, another idea gradually takes shape, one that leaves the engine and its fuel behind entirely, and asks whether light itself can serve as the driving force. The concept begins with a subtle property of radiation. Light carries momentum. Even though individual photons have no rest mass, their motion allows them to push on matter when they are absorbed or reflected. Under ordinary conditions, this pressure is tiny, imperceptible in daily life. But in the vacuum of space, with enough time and a large reflective surface, it becomes a gentle but continuous thrust. A solar sail embodies this principle. Instead of a nozzle at the back of a rocket, the spacecraft unfurls a wide feather-thin sheet of reflective material and turns it toward the sun. Each photon that strikes the sail and bounces away transfers a minute impulse. Over days, months, and years, these impulses accumulate. With no propellant to run out the sail, can in principle keep accelerating for as long as sunlight shines upon it, gradually reaching speeds that would be difficult for chemical rockets to match. Demonstrations within the solar system prove that the idea works. Small test craft deploy modest sails and maneuver using nothing but starlight, their trajectories bending in response to the slow, constant push. Yet when the numbers are traced out toward interstellar distances, another limitation appears. The intensity of sunlight diminishes with the square of distance. Near Earth, the light from the sun exerts a certain pressure. Twice as far away, that pressure falls to 1/4. Far out beyond the orbit of Neptune, the thrust becomes almost negligible. A solar sail can be an elegant engine for travel between planets, but as a tool for crossing the gulf to Alpha Centauri, it loses effectiveness just when it is most needed. To rescue the concept, thinkers reverse the roles of star and sail. Instead of relying on diffuse sunlight, they imagine driving the sail with a powerful concentrated beam of artificial light produced not by a star, but by a vast array of lasers. In this scheme, the spacecraft becomes as small as possible, while the ground-based engine becomes immense. The ship is reduced to two essential elements, a highly reflective sail and a miniature payload. The sail might span a few meters on the side and be only a few hundred atoms thick, made from advanced materials that combine extreme lightness with the ability to endure intense illumination. At its center sits the payload, a tiny chip carrying cameras, sensors, a power source, and a communication system, all compressed into a wafer weighing only a few grams. This wafer sail assembly is not intended to climb from Earth on its own. Larger conventional rockets or other launch systems lift it into space and deploy the sail. Once it is clear of the atmosphere and aligned, the true engine comes into play. On the surface below, in a high dry region chosen for clear skies, thousands of individual laser units act in concert. Their beams are phase-locked and combined into a single coherent column of light that reaches into space. The total power of this combined beam is envisioned at levels comparable to the output of large nations, tens to hundreds of gigawatts, sustained for a few minutes. When this artificial star of focused light shines upon the sail, the result is a force many orders of magnitude greater than that of natural sunlight. Photons from the beam ricochet off the reflective surface, transferring their momentum at a furious rate. The wafer sail begins to accelerate. Because its mass is so small and the applied force so large, the acceleration can be extreme, tens of times the acceleration that humans experience at Earth's surface. No living crew could endure such a push, but a chip with no biology feels no discomfort. For several minutes, the laser stays locked on target, while the sail races outward, its speed climbing from 0 toward a significant fraction of the speed of light. At the end of the firing period, the sail may be millions of kilometers away from Earth and moving at perhaps 20% of light speed. The beam switches off, the lasers cool, and from that point onward, the craft coasts. No further propulsion is needed. At 1/5 of light speed, the distance to Proxima Centauri, a little more than 4 light years, compresses into a travel time of about 20 years, as measured in the frame of the solar system. For the first time in the narrative of interstellar flight, the numbers associated with a journey to another star become comparable to a human career, rather than to the entire span of human civilization. A scientist working on the launch could, in principle, live long enough to receive data from the flyby. In this light, the neighboring system shifts from being only an unreachable abstraction to a plausible target for a technological project. The payload, though tiny, could on arrival return images of Proxima Centauri, of its planet, and perhaps of the wider Alpha Centauri system, sending back measurements of magnetic fields, stellar winds, and atmospheric signatures. Each bit of data would take a little more than 4 years to cross back to Earth at the speed of light, so the full cycle from launch to first returned signal would be on the order of a quarter century. The elegance of the concept lies in how it sidesteps the rocket equation. The spacecraft carries no propellant. It does not lose mass as it accelerates. All the energy and momentum required to push it to high speed come from the external laser array on Earth or in orbit. The fuel, in effect, stays at home. Because the payload is so light, the total amount of energy needed, while enormous, is not beyond imagination for a future civilization that has expanded its power infrastructure. The laser array itself, once built, could in principle launch many such probes along different trajectories, creating a fleet of wafer-sized explorers fanning out toward various nearby stars. Yet this solution introduces new challenges that echo the earlier ones in different forms. The first is deceleration. A craft accelerated to a fifth of light speed by a beam from Earth has no onboard propellant to slow itself when it approaches Proxima Centauri. It cannot carry a second laser. The beam behind it cannot reach across light years to apply a braking force. Under the simplest version of the scheme, the probe therefore flies straight through the target system in a swift arc. Any planet's rings or stellar atmospheres it passes can be sampled only in a few hours or days, after which the craft continues into interstellar space, unable to turn around. The mission becomes a high-speed flyby rather than an orbital reconnaissance. The second challenge, which unfolds more fully later, is survival during the crossing. At 20% of light speed, even single dust grains and sparse atoms of gas between the stars turn into dangerous projectiles. A gram-scale craft with a sail of ultra-thin material must withstand the accumulated impacts of 20 years of motion through the interstellar medium. Designing a shield that can handle this regime without adding too much mass becomes a puzzle as intricate as the construction of the laser array itself. Laser-driven sails therefore represent a different kind of threshold in the story. They do not require mastering fusion or flying giant nuclear pulse ships, but they demand a global or even planetary effort to construct an immense coherent beam and to develop materials at the edge of what condensed matter physics can provide. In return, they promise to collapse the vast timescale of the 70,000-year drift to Proxima Centauri, down to mere decades, turning the closest star from a symbol of impossible distance into a destination that could in principle be probed within the span of a single human life, even if only in a fleeting relativistic pass. As the idea of laser-driven sails matures, attention turns away from the dramatic moment of launch toward the long, quiet years that follow. Because sending a gram-scale craft toward Proxima Centauri at 1/5 of the speed of light trades propellant for a harder question whether anything so small can survive the journey at all. The map between the Sun and Alpha Centauri looks empty. On average, there are only a few atoms of gas in each cubic centimeter, far less than any vacuum created in a laboratory on Earth. Yet that thin medium is not perfectly clean. Mixed into it drift tiny grains of dust, fragments of carbon, silicate and ice. At modest orbital speeds, these grains only pit spacecraft surfaces. At relativistic speeds, they become bullets. The kinetic energy of a collision grows with the square of the speed, so a rise in velocity multiplies the violence of every impact. A dust grain that hardly matters at a few kilometers per second becomes a serious weapon at tens of thousands of kilometers per second. For a probe that weighs only a few grams, a direct hit can be fatal. Over a span of 20 years, a probe racing through the thin gas and dust between stars will encounter countless atoms and a smaller but still significant number of solid particles. Each encounter with dust chips away a little material from the leading edge, a process known as sputtering. To cope with this, designers imagine changing the shape and posture of the craft. Instead of presenting a broad sheet to space, the wafer and its sail are folded and turned edge-on in cruise, so that only the narrowest profile faces forward. Ahead of the main chip on a tether or a rigid spar rides a sacrificial shield, perhaps a thin tile of graphite or other robust material. This tile takes the first shocks, slowly ablates, and leaves a plume of vapor and fragments that may help to vaporize incoming grains before they reach the fragile electronics behind. If sized correctly, such a shield could survive the expected number of dangerous impacts over a 20-year crossing. More speculative concepts extend protection beyond solid matter. A loop of superconducting wire carried by the probe could create a magnetic field, trapping charged particles and inflating a bubble of plasma, an artificial magnetosphere. Neutral dust grains would still pass through, but energetic ions from the interstellar medium and from Proxima Centauri's wind would be deflected. Combined with a physical shield and a needle-like orientation, such a system might give a slender craft a chance of emerging from the crossing with its core systems intact. Radiation is a constant presence. Interstellar space is filled with cosmic rays, high-energy protons and heavier nuclei, accelerated by distant supernova remnants and other violent events. When a probe moves at relativistic speed, particles and photons that approach from the front are blue shifted to higher energies. Each impact can knock atoms out of place in the structure or flip bits in memory. Over years, the accumulation of such hits can damage electronics unless they are carefully hardened and supported by error-correcting codes and redundancy. The wafer probe has very little mass to spare for thick shielding. Every additional layer of material adds weight and demands more power from the laser array to reach the same final speed. The design becomes a narrow trade between protection and acceleration. Make the probe too robust, and the beam cannot push it fast enough. Make it too light, and it may be shredded long before it nears Proxima Centauri. In this corridor between fragility and mass, the engineering problem begins to resemble the biological one faced by any hypothetical generation ship. In both cases, the universe resists the maintenance of complex structures over long times and distances. Survival depends on continual repair and tolerance of damage. Even if the probe endures deceleration, remains the other unsolved half of the journey. A laser sailcraft carries no fuel and has no engine of its own. Once the launching beam fades, its speed is fixed. Without a second beam waiting at Proxima Centauri, stopping becomes almost impossible. Some proposals explore magnetic sails, loops of wire that interact with the stellar wind and magnetic field of the target system to produce drag. Others suggest turning the sail around and using the light of the destination star as a braking force. For a gram-scale craft arriving at a significant fraction of the speed of light, these methods are weak. The star's light and wind do not provide enough impulse over the short time near closest approach to remove more than a small fraction of the kinetic energy. The probe therefore does not enter orbit. It tears through the Proxima Centauri system in a single swift transit, snatching what data it can from a brief window of measurement before sliding outward again into deeper dark. The journey of 20 years is spent in blind endurance. The revelation, if it comes, arrives in a short burst of signals. This imbalance between the long silence of travel and the sharp brevity of encounter captures something about the nature of interstellar flight. It extends a pattern already seen when spacecraft spend months or years cruising through interplanetary space to obtain a short period of close observation at a distant world. Stretched to the gap between the Sun and Proxima Centauri, that pattern turns the long night between stars into the dominant feature and leaves the moment of arrival as a thin bright edge, a passing glimpse of an alien shore, before the messenger fades once more into the dark. Word count 947. Awaiting continue. Bạn đã nói continue, ChatGPT đã nói, đã suy nghĩ trong 50 bước. Section 14. The emptiness between the Sun and Alpha Centauri is not only thin gas and scattered dust. It is also filled with an invisible storm of radiation that works slowly and relentlessly against anything that tries to cross it, turning the long voyage into a contest between structure and decay. Throughout the galaxy, violent events such as supernova explosions and energetic outflows from compact objects accelerate charged particles to near light speed. These particles, mostly protons and heavier nuclei, stripped of their electrons, wander through interstellar space as cosmic rays. On Earth, a thick atmosphere and a wide magnetic field deflect and absorb the majority of them, before they reach the surface. In low-orbit spacecraft, and astronauts experience higher doses, yet still benefit from the partial protection of the planet's magnetic bubble. Far from any planetary shield in genuine interstellar space, there is no such barrier. A starship or probe coasting between systems lies exposed within this flux. Each cosmic ray that strikes matter deposits energy along its path, shattering molecular bonds, displacing atoms in crystals, and sometimes transmuting nuclei. In electronics, a single impact can flip a bit, create a false signal, or permanently damage a component. Over months, the effects can be managed by redundancy and error correction. Over years and decades, the accumulation becomes a central design constraint. Components must be chosen and arranged not only for efficiency and weight, but for their ability to endure countless microscopic blows. For biological tissue, the stakes are higher. Radiation damages DNA and other critical molecules. Cells have repair mechanisms, but these are not perfect. Misrepaired breaks accumulate as mutations, some harmless, some lethal, some that promote cancers. In a generation ship slowly drifting toward Alpha Centauri, every member of the population would receive a continuous dose of this background. Shielding with water, plastics, or rock can reduce exposure. Yet effective protection requires many meters of material. Providing that depth around large habitats adds enormous mass, which must be accelerated at launch. A compromise emerges in which some areas of the ship are heavily shielded as refugees and others are more lightly protected. Life aboard becomes a choreography between safer zones and working spaces, while medical systems monitor and attempt to mitigate long-term effects. The physics of radiation thus shapes not only the hardware of the ship, but the arrangement of its living spaces. The same flux that strikes matter also defines part of the psychological landscape of the long voyage. In interstellar space, the sky would be extraordinarily sharp. Without atmospheric scattering, the stars no longer flicker. Each point is a precise unblinking light, fixed against a dark so deep that the eye never quite adapts. The Milky Way stretches as a bright band dense with structure clusters, rifts and knots. At first, this view might seem overwhelmingly rich, yet over years it would change only slowly. The apparent positions of distant stars would remain almost fixed. Even as a ship covers trillions of kilometers, its motion is small compared to the scale of the galaxy. The only lights that noticeably change are the nearest ones. The sun behind would shrink from a bright star to a lesser point. Alpha Centauri ahead would grow in brightness, but over most of the voyage both would be merely slightly unusual specks among many. For a robotic probe, this unchanging sky is irrelevant. For a human crew, it becomes the backdrop to every memory, a permanent night in which no sunrise or sunset ever occurs naturally. Artificial lighting and simulated day-night cycles would provide local rhythms. Yet everyone aboard would know that beyond the hull, the universe remains in a state of endless midnight. Communications add another layer to this isolation. Close to Earth, messages travel almost instantly. Signals to the Moon take a little more than 1 second. Signals to Mars, depending on alignment, can take minutes. To a vessel halfway between the Sun and Alpha Centauri, light requires more than 2 years to cross the gap in either direction. A question sent to Earth yields an answer at best 4 or 5 years later. Conversation becomes impossible. Guidance from home cannot arrive in time to respond to immediate problems. The ship and its inhabitants must operate as a closed decision-making system, with only the faint delayed echo of contact reminding them that a wider civilization still exists. In this environment, time itself feels altered. Generations would pass knowing that the world of their ancestors lies years away at light speed and that the destination lies the same distance ahead. the idea of belonging to a larger species spread over a planet becomes abstract. Identity compresses into the boundaries of the ship. The physical erosion by cosmic rays and the mental erosion by extreme isolation mirror each other. Both act slowly, incrementally, and both must be countered by strategies that emphasize repair, redundancy, and meaning. For electronics, that means self-checking circuits, backup systems, and software that can detect and correct errors. For a crew, it means rituals, stories, education, and structures that preserve knowledge and purpose across centuries. In both cases, the requirement is not simply to endure, but to endure without losing coherence. Against this background, the 70,000-year travel time implied by chemical propulsion acquires a deeper significance. It is not only a statement about distance and speed, it is a measure of how long complex arrangements of matter must resist the universal tendency toward disorder if they are to carry themselves from one star to another. A robotic wafer sail that crosses the Gulf in 20 years faces the same principle in compressed form. It must maintain its fragile organization while constantly absorbing the impacts of dust gas and radiation, and then perform flawlessly during a brief moment of encounter. A generation arc must extend that discipline across timescales that dwarf ordinary human narratives. In both cases, the space between the Sun and Proxima Centauri is less a neutral gap and more a medium that actively tests the persistence of patterns. The darkness between stars thus becomes not just a visual absence of light, but a field in which time, radiation, and isolation work together to oppose the continuity of technology and life, transforming the idea of a journey into a prolonged negotiation with the basic conditions of the universe. The Alpha Centauri system stands at the edge of human imagination as a kind of cosmic paradox, a neighbor that is at once almost within reach and effectively unreachable. It lies only a little more than 4 light-years away, a distance that sounds modest when compared to the size of the galaxy, and in diagrams, the Sun and Alpha Centauri sit close together, 2 dots separated by a short line. Yet every attempt to translate that line into a journey reveals layers of resistance. Proxima Centauri b, the nearest known terrestrial exoplanet, orbits within a temperate ring that once seems to promise oceans and air, but closer inspection shows a world probably stripped and scorched, locked in a perpetual contrast between a burned dayside and a frozen nightside. Dust, gas, and radiation in the space between the two systems work slowly against any fragile machine or organism that tries to cross it. Existing engines fall short by orders of magnitude when asked to span the Gulf. Concepts built on nuclear fire or laser light shrink the travel time from tens of thousands of years to a human generation, but only by invoking infrastructures and risks far beyond current civilization. In this way, Alpha Centauri becomes a mirror. In one reflection, it shows the hard edges of speed and energy. The speed of light remains a fixed ceiling. The rocket equation quietly enforces its logarithmic constraint. The density of the interstellar medium, though vanishingly low, becomes important when multiplied by the square of relativistic velocities. The nearest star thus demonstrates that the universe does not arrange itself for easy travel. Stars behave like remote islands separated by an ocean whose depth is expressed in time rather than in distance, an ocean that must be treated as part of the structure of reality rather than as a mere technical inconvenience. In another reflection, Alpha Centauri reveals ingenuity. The difficulty of crossing to the nearest star drives thought outward into new regions of engineering. Nuclear pulse concepts, fusion-driven arcs, and light sails are not merely designs for a distant mission. They are exercises in extending what counts as a possible engine, in imagining architectures where propellant stays at home or where a ship becomes its own world. Some of the technologies required for such journeys, such as controlled fusion or coherent laser arrays on a planetary scale, would transform life in the solar system long before any starship departs. In that sense, the unreachable neighbor acts as a distant catalyst, shaping developments that unfold close to home. A third reflection concerns perspective. The harsh environment of Proxima Centauri b throws the particular qualities of the Sun and Earth into focus. A small red star, prone to flares and steep gradients of light and wind, appears capable of stripping a planet of air and water, even while holding it in a nominally habitable orbit. By contrast, the Sun shines with relative steadiness. Earth retains a thick atmosphere and large oceans over billions of years. A magnetic field and a balanced distance from a quiet star work together to maintain a surface where liquid water and complex chemistry persist. The comparison suggests that worlds like Earth may be rarer than simple energy balance diagrams imply, and that the oasis of the solar system is more fragile precisely because the nearest example of a similar-sized planet seems to have lost its gentler conditions. Finally, Alpha Centauri reflects persistence. The system has anchored generations of speculation. Studies of possible missions use it as a reference case. Even knowing that its nearest planet is likely inhospitable does not erase its pull. The very inaccessibility of the three-star system turns it into a long-term project, something that continues to be examined and reimagined as instruments improve and theories evolve. Light from Alpha Centauri arrives at Earth after a few years of travel unchanged by human interest, and observatories collect it, split it into spectra, and search for tiny variations. No craft has yet crossed the Gulf, but information already flows one way in the form of data, and the possibility of future probes adds an invisible second stream in the form of plans. For now, the distance between the Sun and Alpha Centauri remains what physics makes it a gap that chemical engines cannot cross quickly, and that advanced concepts only begin to shorten in imagination. Proxima Centauri b circles in its locked dance of day and night, likely airless and silent. Between the systems stretches the long night of dust gas and radiation. Within that frame, Alpha Centauri serves less as an imminent destination and more as a carefully measured boundary. It marks the scale at which a planetary civilization starts to feel la verdadera size of the cosmos, the point where local ingenuity meets the broader structure of space and time and discovers that some barriers are not yet negotiable. The questions that follow remain open. Will the first emissaries to cross the gap be gram-sized chips riding beams of light, large nuclear vessels crewed by generations, or something entirely different that current thinking has not yet outlined? Will the system always remain a distant mirror, or will some future age see its three suns not only as points in the sky, but as disks overhead? The answers reside in futures that do not yet exist. For the present, the nearest star continues to shine from just beyond reach, a quiet reminder that even in a universe filled with countless suns, the space between them is as much a character in the story as the stars themselves. In the quiet, after the journey, the image of the three distant suns fades to a soft afterglow, and the great gulf between stars settles into a simple backdrop of darkness and scattered light. The mind that has followed these scales of distance and time now drifts along gentler currents, recalling not the harsh details of flares or engines, but only the slow, steady turning of worlds and the calm persistence of starlight crossing the void. Thoughts that once traced orbits and velocities grow slower, less defined, as if they too are subject to a kind of cosmic drag, losing momentum until they float almost weightless. The sense of scale that has expanded outward toward Alpha Centauri now folds inward back toward a single small world under a single quiet star, and then inward again toward a single resting body, breathing in a rhythm that matches nothing more demanding than the rise and fall of a chest. Far away, the nearest star continues its distant, unhurried burning, indifferent to plans and engines, while nearer still, the sun holds its own system in a warm, protective field. Between them, space remains vast and silent, but here in this much smaller space, everything is still. The long night between stars becomes an image rather than a destination, a smooth, dark ocean across which no action is required, only the slow passage of time. Around that image, the last edges of wakefulness loosen and blur. Thoughts lengthen into fragments, then into impressions, then into nothing at all. Breathing remains steady and quiet while the universe beyond goes on in its patient way, with stars shining and planets circling untroubled by the sleep that now arrives. The journey pauses here, held gently in the dark, while the cosmos keeps watch from very far away.